Hello, my dear students, and welcome back. I know, exams are super close, and seeing a chapter called Nuclei can give a little bit of tension, right? But please, tension mat lo, we are going to make this chapter so simple for you. Just stay with me, and together we will aim for full marks. Pakka.
So, here's our game plan for today. A simple, 6-step roadmap to completely master this chapter. We'll start from the very basics and go all the way to solving an actual exam question. Looks like a lot? Nah, trust me, it's a piece of cake. Cello, let's begin.
Okay, first stop. We're going on an adventure. We're shrinking ourselves down smaller than a grain of sand and diving deep inside an atom, right into its center, its tiny beating heart. We are going to meet the nucleus.
Now, just to give you an idea of how incredibly tiny this nucleus is, just imagine the classroom you're sitting in, okay? Imagine that whole room is one single atom. Now look for a tiny little pinhead right in the middle of the room. That's the nucleus. It just shows you an atom is almost completely empty space.
But here is the absolutely mind-blowing part. Are you ready? That tiny pinhead contains more than 99.9% of the mass of the entire classroom. Can you believe that? It's unbelievably small, but it's where all the weight, all the substance of the atom is packed. It's super dense.
So the big question is, who lives inside this tiny, super heavy house? Well, it's time to meet the residents. Let's call them the nuclear family. These are the particles that make up the nucleus.
First up, meet the big brother of the family, the proton. He's the positive one, always full of positive energy. He carries a positive charge. And the number of protons, well, that's like the atom's roll number, or its Aadhaar card. It gives the atom its unique identity. We call this the atomic number, or just Z.
Next, we have the proton's calm, cool, and chilled-out brother, the neutron. As the name suggests, this one is neutral. No charge, no drama. He's just there to add some weight and keep things stable. His discovery by the great scientist James Chadwick was a total game-changer in physics.
And when you count all the family members together, all the protons and all the neutrons, what do you get? You get the mass number, which we write as A. So it's a very simple formula, A equals Z plus N. And this whole family, the protons and neutrons together, get a family surname. We call them Nucleons. Simple, right?
Now, bachcho, full focus here, okay? This table is super duper important. A question from this part is almost pakka. I'm telling you, it will come in your board exams. So listen carefully. Isotopes have the same number of protons. Isotones have the same number of neutrons. And isobars have the same mass number, or A. I like to remember it as bar for weight. So isobars have the same bar. Just remember P, N, and A, and you will never ever get confused. Promise.
But wait a second. Let's think about this. We have all these positive protons, right? And they are all squeezed into this tiny space. And we all know that positive charges repel each other. They should be pushing each other apart so hard that the nucleus just explodes. So what is this magic glue that's holding them all together? Let's find out.
And this leads us to a really strange puzzle. It's like a magic trick. If you take, say, 2 protons and 2 neutrons, and weigh them separately, and you add up their weights, and then you weigh the nucleus they form, you'll find that the nucleus is always a little bit lighter. How is that possible? Where did that little bit of mass just disappear?
Now, this isn't a mistake. This missing mass is a real thing, and scientists have a cool name for it. It's called the mass defect. We show it with the symbol delta M. It's simply the difference between what the parts should weigh and what the whole thing actually weighs. So where did the mass go? Well, the answer to this amazing puzzle was given to us by the genius of all geniuses, Albert Einstein. And he gave it to us in his world-famous magical equation. You've seen it everywhere, right? On t-shirts, in movies. E equals mc squared. This is the formula that connects mass and energy. So here's the secret. That missing mass, the mass defect, it didn't just vanish into thin air. No, it got converted into a huge amount of energy. And this energy is the magic glue. It acts like a super strong fevicol, holding all the nucleons tightly together and overcoming that repulsion force. And this, my friends, is what we call binding energy.
Okay, team, screenshot this with your brain. This graph, this is the heart and soul of the entire chapter. It's called the binding energy curve.
I know, it looks a bit complicated, but please don't get scared. It tells a very, very simple story about which atoms are stable, which are not, and most importantly, how we can get energy from them.
So, what is this story? Look at the peak of this curve, like the king sitting on top of a mountain. Who's there? It's iron. Iron is the superstar of stability. The nuclei in the middle are the most tightly bound, the most stable, the happiest. But you see the elements on the far left, the really light ones, and the ones on the far right, the really heavy ones? They are less stable. You could say they all have FOMO. They all want to be more like iron.
And this desire, this need for the unstable atoms to become more stable, well, that is the secret behind unlocking unbelievable amounts of energy. And this happens through two very famous processes that you've definitely heard of: nuclear fission and nuclear fusion. First up, let's talk about fission. This is what happens inside nuclear reactors. You take a really heavy, unstable nucleus, like uranium. Think of it like a giant wobbly lotto. It's just not stable. Now, you gently poke it with a tiny neutron and bam! It splits apart into two smaller, lighter nuclei. And because these new, smaller nuclei are more stable, they've moved up on our stability curve, a huge amount of energy is released.
And on the other hand, we have fusion. Now this is what powers our sun. It's the ultimate energy source. Here, instead of breaking things, we build things. You take two very light, unstable nuclei, like hydrogen, and at crazy high temperatures and pressure, you smash them together. They fuse to form a heavier nucleus, like helium, which is way more stable. And in this process, even more energy is released than in fission. It's just incredible.
All right, enough of theory. I know. The moment we see numerical problems, some of us get a bit scared. But please, don't worry. The sums in this chapter are based on very simple step-by-step logic. So let's build our confidence together by solving a typical exam question. We can do this. Let's go.
Okay, so here's our question. It's a classic one, straight from your NCERT textbook exercises. We have to calculate the binding energy of a nitrogen-14 nucleus. And they have very nicely given us the actual measured mass of the nucleus.
Now, the first thing we always do is check our toolkit. What information has the question given us? Okay, we have the mass of the nitrogen nucleus, we have the mass of a single proton, and the mass of a single neutron. And look, we have our magic key, this conversion factor that turns mass into energy. This MeV just means mega electron volts. Think of it as a packet of a huge amount of energy. Perfect, we have everything we need.
Okay. Let's break it down. Just 4 simple steps. Step 1. Let's find our family members. The symbol tells us everything. The bottom number, 7, is the number of protons. The top number, 14, is the total. So, neutrons? That's just 14 minus 7, which is 7. So 7 protons and 7 neutrons. Easy. Step 2. Calculate the mass of all the parts. Let's find what the nucleus should weigh. We'll multiply 7 by the mass of a proton and 7 by the mass of a neutron and add them up, and we get 14.11534 U. Remember this number. Step 3. Find the missing mass, our mass defect. We just subtract the actual mass they gave us from the mass we just calculated. The difference is 0.11236 U. See? A tiny bit of mass is missing. We are almost done. Step 4. Time for the magic. We convert this missing mass into energy. We take our mass defect and multiply it by that magic number, 931.5, and our final answer is 104.66 MeV. That's it. 4 simple steps, full marks.
And there you have it. We went inside the atom, met the nuclear family, and uncovered the secret of the universe's strongest favicole, the binding energy. And we saw how breaking or building atoms can release that energy. See, you are all absolutely brilliant. You have completely understood this chapter. You've got this. Bakka, go and rock your exams. All the very best, my bachcho.